Here's a question that sounds simple. How fast can we travel in space? Not our probes, not our satellites, us, human beings, in a ship, arriving somewhere still alive and still sane. That turns out to be a completely different question from how fast can we build something to go. Our fastest machine, the Parker Solar Probe, hits over 400,000 miles an hour. No human has ever gone anywhere close to that, and for a very good reason. The thing that actually limits how far and how fast we can travel isn't the rocket, it's us. So let's start with where we've actually been. The furthest any human has ever physically travelled from Earth is the Moon, about 239,000 miles away. That's it. That's the entire human travel record, and it was set over 50 years ago. Every astronaut since, everyone on the International Space Station, everyone who's ever lived up there, has stayed in low Earth orbit, closer to home than a short-haul flight. The longest anyone has stayed in space in one stretch is 437 days, a record set by Russian cosmonaut Valery Polyakov aboard Mir in the 1990s. NASA's own longest single mission by astronaut Frank Rubio was 371 days. Both of those numbers matter more than they sound, because they're not test results. They're close to the actual limit of what a human body can currently endure. Here's why that limit exists, and it's the real subject of this video. 3 things break down the longer you're in space, and none of them care how fast your rocket is. Radiation is the big one. Once you're outside Earth's protective magnetic field, you're exposed to cosmic radiation, with essentially no shielding beyond your spacecraft's walls. With current shielding technology, researchers estimate astronauts can spend roughly a year in deep space before the accumulated radiation dose becomes dangerously high. That's not a soft guideline, it's close to a hard ceiling. Bone and muscle loss is the second problem. Without gravity working against you, astronauts lose bone density at around 1 to 1.5% per month, and can lose up to 20% of muscle mass in the first month alone without serious daily countermeasures. NASA fights this with hours of resistance exercise every single day, but it's management, not a cure. And then there's the psychological side: isolation, confinement, and total distance from Earth in a metal box with the same handful of people for months on end. NASA has an entire framework for these combined risks, nicknamed RIDGE: radiation, isolation, distance, gravity, and hostile environment. Every one of those 5 gets worse the longer the trip runs, so put a number on it. If a year in deep space is roughly the ceiling, how far does that actually let us go? This is where Mars becomes the honest answer, not because it's exciting, but because it's close to being the only place we can currently reach and come home from within that limit. Using today's standard chemical rockets on the most fuel-efficient trajectory, a one-way trip to Mars takes somewhere between 6 and 9 months. Add the months you'd have to wait on the surface for Earth and Mars to realign for the return journey, and a full round-trip mission runs to 2 or 3 years, which pushes well past that 1-year radiation ceiling, using nothing but current, already built technology. This is exactly why NASA is putting real money into nuclear propulsion. A nuclear thermal engine, the kind currently being developed and tested under NASA and DARPA's Draco program, could cut that one-way transit down to somewhere around 3 to 4 months. That's not a minor improvement. It's the difference between a mission that fits safely inside the radiation budget and one that doesn't. So genuinely, how fast can we travel in space? With the technology sitting on the drawing board right now, nuclear thermal propulsion, better shielding, serious daily exercise regimes, a crewed round trip to Mars in around 2 years, with each leg taking 3 to 4 months, is a realistic, survivable target within the next couple of decades. That's the actual frontier. Not Alpha Centauri, not another galaxy, Mars, and only Mars, because it's the furthest place the human body can currently make it to and back from in one piece. Everything past that isn't a rocket problem anymore. It's a body problem. Faster engines get you to Mars sooner. They don't fix radiation, and they don't fix a year in a metal box with 5 other people. Fixing that comes down to 3 things, and they're not equally close to being solved. Artificial gravity is the closest to real. Spin a structure and you get gravity. That's not new physics. It's been understood since the 1960s, and it's mostly an engineering and cost question now. How big does the structure need to be, and how fast can people adapt to the spin without getting sick? Recent research is encouraging. Astronauts can adapt to faster rotation than once thought, given about 50 days of gradual training, and mission designers have already sketched workable designs, like a 50-meter rotating structure giving continuous Earth gravity for only a small mass penalty. A private venture even broke ground in 2025 on a rotating station in low Earth orbit to test exactly this. This is the one most likely to be flying in some form within the next decade or two, and it directly fixes bone and muscle loss, the best understood of the three problems. Shielding is real, but it's improving in small steps, not one big leap. Hydrogen-rich materials like polyethylene, or even just the water a ship already carries, cut radiation exposure by around 10 to 20% compared to a standard hull. But real protection needs a genuinely thick layer wrapped around the crew, and every extra kilogram is expensive to launch. The more exciting idea, generating an artificial magnetic field around the ship to deflect radiation, essentially copying what Earth's own magnetic field does for us, is still experimental and a long way from flying. Shielding will keep getting better. It's unlikely to fully solve the radiation problem on its own anytime soon. Medicine is the least mature of the three. There are existing bone density drugs being trialled for astronauts, and at least one radiation injury drug already approved for other conditions that shows promise as a countermeasure. But none of it is routine yet. Side effects limit how long some of these drugs can be used, and several of the most promising ones are unstable enough that they degrade before a 2-year Mars mission was even over. This is genuinely still lab stage work. So here's a hypothetical to close on. Say we get there, shielding and artificial gravity solved to a level we're genuinely comfortable with, and medicine mature enough to handle what's left. What changes? The honest answer is that it changes what kind of engine becomes usable, more than it changes any single number on its own. Right now, propulsion choices are shaped around keeping the trip short, because the human body sets the clock. Once that pressure eases, a different category of engine becomes worth using. Electric propulsion, which produces very low thrust but can run continuously for weeks, gradually building up to far higher speeds than a short, powerful chemical or nuclear thermal burn ever could. The most concrete example on the table is Vasaimer, a plasma rocket concept from Ad Astra Rocket Company, powered by a 200 megawatt nuclear electric reactor that doesn't exist yet at that scale. On paper, it could accelerate a ship to roughly 123,000 miles per hour, about 198,000 kilometers per hour, nearly 4 times faster than any chemical rocket has ever managed, cutting the one-way trip to Mars down to somewhere between 39 and 45 days. A round trip, door-to-door, could in theory drop under 6 months total instead of 2 to 3 years. Worth being straight about this one though, it's a genuinely serious engineering proposal, not science fiction, but it's also disputed. Independent analysis has pushed back hard, calculating that the engine and its power system would need to be many times lighter than anything built so far for those numbers to actually hold up, and a reactor at that power level has never flown. So take it as the most concrete answer to how fast, hypothetically, rather than a promise, in a future where the human body is no longer the limiting factor, roughly 200,000 km/h, and a 6-week trip to Mars is the number worth aiming at, but the engine to get us there is still sitting on a whiteboard, not a launch pad. If you found this useful, hit subscribe for more of these, and a like genuinely helps the channel more than you'd think.